There's no sound.
Yeah, that's fine. Um, it's not. It's cool music, but we can skip it. What matters is the visual. So you can see it's a fighter jet, an anti-gravity fighter jet, um, with some ionic propulsion. But the stealth propulsion part is the part that I handle, and it's pretty. It's relatively easy. It's again, it's a thousand times more efficient than the DARPA pump uh, propulsion, the second best stealth propulsion that there is on the market. Um, so I wanted that was my intro because it's a really cool presentation. A very very important presentation that I'm gonna do. So so I go here. So I'm gonna start. I'm gonna start by talking about the laws. You know, the Newton's third law. Um, to every action, there is always opposed and equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. So it seems simple and some mathematical abstraction law by Newton. It doesn't seem very important. They teach you that at school, and it seems very trivial. But actually, that law is extremely valuable, extremely important because that's not just a mathematical abstraction. It can be converted into um, a real reaction. So it's a real effect. That's what it is. And Newton discovered that in the 17th century. I think that Newton is the smartest guy of all time. That's for sure because that's very non-intuitive to figure that out. And it not only that, but again, it matches a real effect that can be physically measured. And I think that's that's amazing. I just figured that out today, how important that law is and how valuable it is. And like I was saying last week, the energy density law here that Maxwell invented is totally nonsense. It's garbage, total garbage. Why? Because you can see the electric field squared plus the magnetic field squared, um, and then you end up with some energy density. First, a magnetic field and a magnetic field and electric field. Those are gradients. So if you want to have the energy or density out of the gradient, you need to integrate it. So you need to have the integral of the magnetic and the electric fields. So it's completely misleading, confuses everybody. People think that Maxwell is a genius. Maybe he is for some stuff, but not for this equation. For that's for sure. That's the problem with the scientific community is they assume because people figure something out that everything he did is 100% right. Um, but well, the
Now,
truth is,
was it Oliver Heaviside who simplified his equations and threw out some of them, or was that somebody else?
yeah, heavy side fix that, and there's somebody else. I forgot the name. Degen on the APEC chat told me about it. Uh, um, I can check the chat later, and I'll let you know.
Oh yeah, no, I was just wondering because I did come across that in some of my research as well, but I don't know too much about Maxwell himself.
Yeah, that's. But yeah, that's a misleading equation. So that's the problem with science. Like I was saying, I keep saying like almost every week. Uh, the Nobel Prize is epicyclic. So the more we evolve in time, the more difficult it is to prove to convince the community that Einstein is wrong and Maxwell is wrong. And all these rude people. That's the problem with the scientific community. Um, so the Nobel Prize is actually doing the opposite of scientific innovation. It slows down scientific innovation.
Yeah, they could be targeting it and slowing it down.
Yeah.
There's evidence that they did
sure.
with the Rockefellers. They were responsible for dumbing down Americans for sure. I would trace it back to the Rockefellers.
Totally, 100%.
Yeah, they edited our textbooks and all that. Yeah,
Mm-hmm.
insane.
Well, they also
believe it.
took the ether off the periodic table.
Oh wow, I didn't know that.
Dude.
Yeah.
I didn't know that either.
Where can I find the original periodic table that includes the ether?
You might be,
Hey,
I don't know, maybe you might
dude,
be able to find it.
Ben, the Mendeleev,
removed, I
the guy
believe,
that invented it,
1905.
Mendeleev, the guy that invented the table of elements, thought there was an ether. It
right.
bugged him. He was like,
He was
"There's
a
got to
Russian
be
guy.
something like right before hydrogen,"
Interesting. No, I thought I did read something about that briefly a long time ago that you mentioned it. But yeah, that would be awesome to find a periodic table that includes the ether.
Right.
Yeah,
Maybe we'll just make
Mendeleev,
one.
he was a Russian guy, and he was the one who came up with the original periodic table, which included the ether. And then when that reached the United States and academia, and then when the Rockefellers took control of all publications and all the, basically what we see and read, they took control of it, and they basically say, well, if you can't see it and you can't touch it, it doesn't exist.
Yeah.
Well, how friggin' ignorant is that?
Yeah.
It's the same thing with the equations in Oliver Heaviside. Like if you can't measure it, then they just throw it out of the equation.
Yeah. But by the way, Ben, the name of the guy that corrected Maxwell's equation is Lee Hively, Hively, and Lee Hively. So that's what Dijon from the Epic chat said.
I got a twist on Maxwell too, if you want to hear it, Ben.
Yeah, let Philip finish his presentation.
Yes.
Yeah. Let him finish, and then after that we can go nuts.
Yeah, my bad. I'm so sorry.
No problem. And so what I want to show tonight mainly are all these experiments that I made over the last 2 or 3 years. Remember my free fall experiment, but I have the exact mathematics behind it, and it's actually a symmetric recasting of the Lorentz Force. So that's what's happening. I don't invent anything. The Lorentz Force is tested; it works, but it's just misapplied. But if you apply it correctly, you're gonna have two force vectors with the Lorentz Force. I'm not gonna say why because that's still a trade secret for the moment. But
is it kind of like it applies differently, similar to how the laws of thermodynamics applies differently to closed versus open systems?
Yeah, it's not a closed versus open system. It's actually people minimizes these laws, but these laws the Lorentz Force they apply everywhere. It's not just a magnetohydrodynamics. It's not like the Lorentz Force just applies to the magnetohydrodynamics vortex and things like that. It applies everywhere. Not only that, but there are multiple. There's more than one force vector.
So it changes like the centrifugal force of the degree of freedom on what vector you're measuring.
I was gonna say, if you don't mind, if you spun the disk, it would have higher effects.
Yeah,
right?
so that's what I'm showing right now. So the free fall
I'm getting
experiment.
into that too. We got to work together.
Yeah,
I want to do that. I'll do that. I'll reproduce what you want.
Cool.
You know what I mean?
Yeah.
I'll engineer it.
Yeah.
So
But I already tested it, and I have all the statistics.
Yeah, I saw the drop experiments. Those were awesome.
Yeah. And so that's the free fall experiment. So the magnet is not only slower, the neodymium sphere is not only slower than the steel ball, but it also accelerates horizontally. So there's a lateral force. There's a lateral force on the magnetic ball. I just figured that out this week. It's true that, and I verified it with the artificial intelligence to compound my statistics, and it's true. There's a lateral force when the magnetic ball falls. So there are two force vectors with the Lorentz force. Same thing with the MHD vortex. But when I did my MHD vortex experiment, the error I made is I used two magnets. I wrapped the gallium vortex with two magnets. So that kind of cancels the magnetic field, because the magnetic field is a gradient, and when you have a uniform field in it, then you don't have any gradient, so you're not gonna have any force. So it's not gonna, the gallium is not gonna spin. If it spins a little bit, it might be some side effect, but it was not 100% force. So
may I ask you, Phil, do you feel like the magnet's dragging through like an ether as it falls to give it like that? It seems like it's slowing down as it falls.
Yeah, you know what? Actually,
it's got less acceleration.
Jarvis, actually, now that you mention it, Ken Wheeler, he made a device. It has a little battery. He's got a 2-ring magnets, I believe, and I think there's a coil or something involved in it. And he says when you hold this device and you let it slide this way, when you're going down like on an angle like this, he says there's a repelling force. It's really weird. He says it's like, when you put two magnets together and you feel that spongy feel in between the two magnets. Well, it's like that when you hold this little device and you force it down on an angle. When you do that, you're getting the same sensation as if you're putting two magnets together and they're rebounding off the.
Do you remember flux. The term gating, Mike?
Yes. Yeah.
Yeah, it's gating, so. Right? You're right.
Yeah,
it's gating. You know what I mean?
Mm-hmm.
That gating is what they are doing there.
What you call the ether is actually the gravitoelectric field, which is an energy gradient. So it's the same thing as a magnet or electric field or
right.
Gravito-magnetic field.
So when you're passing your magnet through the ether, right, and the gravity responds to that energy source, it's manipulating it. There's interaction constantly.
Exactly. So you have a Lorentz that induces a Lorentz force.
The Lorentz force, I would argue, is something that can explain the dynamics of solar systems. I think the Lorentz force is like the unified force.
Yeah, it's more common than people think. It's not just the MHD vortex and the what's the name of the movie? The Red Submarine with Sean
Red Dawn. Red Dawn.
Oh yeah,
Red Dawn.
That was a good one.
Yeah,
yeah. That's God. That goes back early '90s. That movie.
Yeah, but the Lorentz force is more than that. It applies all the time, all over the place, and it's more important than people think.
Absolutely.
And it's the same thing. The same thing with the grinder on the balance experiments that I made and the spinning wheel experiment. Yeah. I'll show.
Even the gyroscope. When you're spinning a mass object at high speed, and you try to flip it, flip the axis of it, there's a force there that's preventing you from doing it. So when you're spinning a wheel, you're not thinking that there is something coming off the wheel, but there is.
Yeah,
This is where a lot of people don't understand. When you're
exactly.
spinning a wheel at high RPM, that force is being pushed out on the longitudinal, I guess.
Yeah,
Right?
that's the Lorentz force induced by the gravitoelectric field or gravity or ether, same thing. So that's what's going on. And I got the comparison table here of my predictions and the observations.
By the way, sorry to cut you off, Phil. They actually use these gyroscopes on the International Space Station to keep the orientation of the space station in a certain way.
Yeah.
So they're using it on the space station.
When I think about it,
it's called. Is it what's called the? It's hold on. It's called the DZH Dzhinbiskov effect. Right? Am I saying it wrong?
Like a gyroscope. I would say it's a gyroscope.
It's a
how do I
gyroscope.
say? Yeah, but on the International Space Station, the axes flip. You know, like they dropped a tool that had like I don't know, looked like an L shaped or like a T shaped, and the rotation would flip. I don't know if I could show the video here, but you know.
Yeah, we'll carry on with Philip's presentation. Sorry, Phil.
Yeah, but you guys make me think. I'll do some mathematics on the gyroscope while I'm at it. I just forgot, but I can't do that easily.
I want to work with you backstage, man. I think me and you can do some cool stuff.
Yeah, cool.
All right.
Yeah. So here's the prediction of the free fall. Actually, I'm with the mathematics. I'm predicting 17.5% of the deflection with the gravitational acceleration, and the observations it's 18% of deflection, which is pretty close. The MHD actually, since you only need one magnet and not two, and because to generate a gradient, so I screwed up that experiment. So the prediction is zero net force, and the observation is within the uncertainty or zero. So all makes sense. And I did the neodymium ball flip also on a high precision balance. I did observe a 29 milligram of weight shift just by flipping the magnetic ball on the balance.
Well, that's interesting.
Yeah, and the grinder was going at 7,000 RPM, and there was a weight increase actually. So I need, but the grinder is more complex. There's more engines in it, and there are more side effects. So it's cool. It's a cool experiment, but it's not simple enough. You know what I mean? Because there are two.
If I may say, you said one time that you had an idea for a hoverboard, and I think you do. Like, wouldn't that be so cool if you could do the hoverboard, dude?
Yeah.
I can see what you're saying, dude. That's awesome.
Yeah. The hoverboard is similar to the MHD vortex experiment, but done correctly. And I have an alternative of the MHD vortex also I would like to try, but the MHD vortex is not as bad as people think because again the Lorentz force is two vectors and the spinning of the gallium is one force vector that it's kind of wasted, but
you don't have to use gallium though.
Yeah, you can use mercury, but gallium is more safe.
Yeah, but you can use an electrolyte too. Electrolytes are really conductive. You don't have to use the liquid metal.
Yeah, cool.
Right.
I'm the king of electrolytes.
Anything that's conductive, you can spin like that, right?
Yeah.
You don't have to spin a metal. I mean, metal's optimum because
there's a couple of things you can use, Philip, for that experiment. I'll talk to you about that offline.
Cool. All right. Thanks, guys. So these are the statistics of the free fall experiment. So it's kind of an average of all experiments where the magnet was launched with some polarity up and then the polarity was down. So there's a slight difference, but the major difference is between the steel ball and the magnetic ball, where the magnetic ball falls clearly slower than the steel ball. I did try that experiment 40 times, so it's not a simple glitch, you know.
Phil, do you mind me asking, was there a difference if the South Pole is down compared to the North Pole down?
Yeah, that's what I'm saying here. There's a slight difference when you flip the polarity of the magnet. So it's kind of that's what we see is the net result, but the magnetic strength, the polarity, orientation, these are all adding up. You know, these are components adding up to result in a net effect that we see here. So this is the acceleration versus time, and this is the acceleration gradient. That is basically, there's noise clearly, but basically the acceleration gradient is null. So the acceleration changes by with the altitude. That's what I'm saying. So every
It makes sense.
yeah, every height that the ball is, the acceleration will be different.
Yeah, I mean, as you go higher in atmospheres,
Exactly. Yeah, and it's not a constant acceleration. So where was I? Yeah, so I want to now I'm gonna show I'm gonna show again. I showed that this last week, but I'll show it again. But the ball on the left is actually, you'll see it's slower, but it also deviates horizontally. So there are two force vectors caused by the Lorentz force.
Interesting.
Yeah,
It'll
look at that.
deflect.
Yeah.
Wow.
See the magnetic ball? It's not attracted. It's not
It's
attracted to the
experiencing
steel ball.
drag. It's
Yeah,
got drag.
There's a big
That's crazy.
difference. You can see
Yeah.
a big difference. Yeah.
It's dragging
Yeah.
through the ether, dude.
So
It's
the vector,
dragging.
the horizontal and the vertical and horizontal vector force.
That would be
you can
Lorentz.
see. Yeah.
Yeah.
You see the steel ball that doesn't move horizontally at all on the right, but the
Yeah.
magnetic ball is kind of deviating horizontally, and it's clearly slower than the steel ball.
I personally
Yeah,
think
that's
this is a
insane.
very good demonstration of the ether
Yeah,
Yes.
action.
It's
Yeah, that's-
dragging.
yeah.
It's very simple, and you can clearly see that the two are different.
Yeah,
Yeah, they're the same mass. The only thing that's different is one's magnetic and one's not.
And
exactly.
it's like falling
Wow.
slower. So it's hitting space.
Yeah. So I did again. I did, and it's not the startup time. Yes, there's eddy currents in the coils on the top, where I launched the balls, but the startup time, the difference, the delta V, the delta speed, initial speed doesn't make a difference, because I did regressions of the statistics. So the regression, disregards take the initial speed difference. So it doesn't matter if the balls are launched exactly at the same time or not, because the regressions takes care of the statistics.
Yeah,
So-
with the calculation, if you regress it, it would equal, but it's kind of like a acceleration, right?
Yeah, so the regression confirms the exact acceleration that the balls are falling, and they're different. And again, that's not a glitch. I did that experiment 40 times.
I think
Nice.
what a lot of people also don't take into account too, not only is falling through the ether, there's also very random charged particles that are going past this magnet on the way down. And
True.
if that happens, there's an interaction of repelling.
Hey, Mike, what do you
Especially-
think if the magnet were made into an electric too?
Well, yeah, that definitely, most definitely, yes.
Would that be
And
a
oxygen
cool
is
experiment?
paramagnetic as well, so and that's everywhere.
Yeah,
Yeah.
well, the magnet in a copper tube was already done, but the eddy current slows down the magnetic ball from
Do you
falling.
think if you compared like a pendulum between both of
Yeah,
those,
good
oh,
point.
yeah,
I
that would
wanted to
be
do.
cool, dude.
I
Get
wanted
a
to do
laser.
the.
Get a
Yeah.
laser.
Yeah, I wanted to do the pendulum experiment
Dude, you
this
gotta
week.
do that, dude.
I wanted to do the pendulum experiment this week. I think
Yeah.
I did research on it, and the twisting version, the
Torsion.
torsion version of the pendulum is the most precise one,
Yeah.
and that's that you can test the equivalence principle with high precision with the torsion
I would.
pendulum.
I think you should build that because I think you'll be able to
Yeah.
make a lot better mathematical equations using that pendulum.
Yeah,
I think
yeah.
that might actually be a very good tool.
Yeah,
Oh yeah. That'd be cool.
yeah.
It's a cool demo.
Yeah, and I want to do that by this week, but I said, well, I don't know. I already have clear evidence, but if that's not enough, then next time I'll do the pendulum, the torsion.
Do you think
pendulum.
there's like between the ionosphere and the ground, they say there's 100 volts per meter, like regular
Yeah,
atmosphere, right?
Yeah,
So I'm thinking like if there's a natural voltage like that, like we have the potential just powered by the sun because it's like stripping off practically
Yeah.
electrons from our atmosphere, keeping the ionosphere positively charged with the negative.
You
So
know
we
what I
got
think?
100 volts
Philip,
per meter, bro.
Mm.
That's nuts.
yeah.
Like we
And
always
here's-
build things sideways, right? What if
Yeah.
we started building it upwards?
Yeah. So
The design
Jarvis, what I think it would be a really cool experiment if you could actually pull it off is do the same experiment that Philip has done with the magnets, but do it at a way higher elevation. As you say, it's 120 volts per meter, right?
Mm.
So say
I'm gonna
he
make
could
it
find
into an electric too, though. I want to study electric.
Sure, you would get the same effect.
Do you
If
guys
not,
think
No, no, no. The
different
electric's gonna-
longitudes and
I think the
latitudes
electric will delay
make
it
a
too.
difference?
If it were negative, if the electric around the magnet were negative, it would delay it a little bit because compared to the ionosphere, the ground is negative, so it's kind of delaying with the magnet, so it should delay a little bit more. If it were positive, it might go faster because it wants to be attracted to the ground. So
Yeah.
monopolar electrics with the magnet drop would be key, and then pendulum would be really cool.
Oh, here's an
Pendulums.
idea.
It's
Here's an
good.
idea, Philip. So you get your magnet right on the inside, and then you make a ball on that's surrounding that magnet made of an electret.
yeah.
That's what I'm thinking.
Okay, let's talk about that, Mike. I need more details, clearly.
Yeah, I got a great idea on that one.
Cool.
Do you see what I'm saying?
So what you do is you can like from Michael's art supplies, you can buy styrofoam balls. So what you do is you drill a hole to the center of it, hog it out so you can fit your magnet in there, okay, and then you seal it up with tape, and then you build your electret around the ball, the
That'd be nice.
styrofoam ball.
That's a good
Yeah.
idea.
Then you zap it with say 100,000 volts. Charge that electrode up as much as possible, and then drop it.
Yeah,
Interesting.
that's a great idea.
Yeah.
That just came off the top of my head.
That is
Yeah.
awesome, Mike. That was
Nice.
good.
Yeah, it's great that it's recorded because I'll review what you said correctly.
Yeah, and just go to Michael's Art Supplies, and you can pick up styrofoam balls that are like 6 or 8 inches in diameter. Drill out the center of the ball. Put your magnet in there, seal it up, and then do your layers to make an electret. Like what is it? They use tin foil and paraffin wax, kind of like the way Townsend Brown was making his isometric capacitors, like that,
Yeah.
right? And then zap it with a high voltage wand, charge it up, and then drop it and see what happens.
Yeah.
Yeah.
Nice.
I have all of those materials you're talking
Dude,
about.
we're gonna have to talk
All of
about
them.
that backstage.
Like
Yeah.
you're talking. I have all of the stuff already. I
This
got
is backstage material.
Nice.
Yeah.
no,
this
like
was,
even the wand the other day we got this like little fly swapper, but it has high voltage.
Oh yeah,
You
yeah,
know,
I
like
got
the
one of
little
those.
like looks like a racket, but then
Yeah, I got no. There's a funny story on that. The first time I got one of those tennis rackets, fly swatters, I was in the Philippines, and I never seen this thing before. I go, a tennis racket? What is it? She goes, oh, it's to kill flies and bugs. It's electric. And I go, oh, cool, like
Nice.
a zapper. And she goes, yeah.
Nice. So yeah, I just want to show also the grinder experiment that I done 3 years ago. That I didn't show on that show here. So I'll show it officially now.
All right. Anything happen? Is it working?
So you clearly see that the weight changes when the grinder spins at 7,000 RPM. But the grinder is not the same. There are many side effects and components, so it's not a simple toy. So you might have like residual
Yeah,
forces.
you're gonna have torque, so it's gonna want to spin, like twist on its own.
Yeah,
right?
but that's because of the like I was saying. That's because of the Lorentz force. There are two
Right.
force vectors. One force vector to make the grinder spin on itself, and the other
Right.
the other vector that reacts with the gravitoelectric fields or gravity vertically. So it's either gonna gain or lose weight, and that's my MHZ vortex here.
Yeah, you did this 2-3 years ago. It's been a while.
Yeah. But the weight changes, but again, I'm using two magnets. I should have used one. So that was
Right.
my mistake. The effect would have been much stronger if I used just one magnet. And this is
Yeah. Yeah, this is the video. Yeah,
this
watch
is the
this.
one. Yeah.
Now that weight is like 45 pounds. See, look at that. One arm, he's twisting 45 pounds of weight. So he spins it real fast, and those forces basically reduce the mass of the object. Now, you notice it only really works when it's in motion. Okay,
Yeah.
you could spin it. It has to be in motion.
Yeah, that's because of the Lorentz forces again. That's
Can you imagine having, say, like a regular, say, fighter jet, and having two of these things spinning at like 100,000 RPM, and the jet's got the propulsion going forward. So now you got that force going, and it's in motion. That would reduce the mass gravity effect of the plane.
exactly, and that's what's kind of repressed by the mainstream scientists because they don't
That's
understand
crazy.
it. They
You
don't
know what?
understand it, so they don't harness it.
You know
what
what?
if there
I might
was a
actually,
wheel? Like, what if there was a rotating wheel, and if he's standing on a rotating wheel and he does this, would the wheel naturally rotate as well?
yeah, yes,
Right.
it will.
Like
Yeah.
underneath him, yeah. If you like
Yeah, it will.
okay.
Yeah, you just saw. You can't even lift it on himself when it's
See,
not spinning.
when you, even if it's spinning, okay, you spin that wheel up to several thousand RPM. If he's just holding it like this, nothing happens. It's when it goes into motion.
Yeah,
When it goes into
exactly.
motion, that 45 pounds has probably gone down to 5 pounds.
Yeah,
But it has to be in motion.
yeah,
I think
exactly.
that's the key.
Yeah,
See? Watch.
that's exactly
Watch.
it. But
See, he's going to spin it up. Now, when it's